All right, let's get started. So last class of the semester. The final you should already know, but in case you don't know, I'll show you how easy it is. So if you do humane, so spring 2024 final exam is the first link. This course is EET 325. So I just type in search for EET. And then EET 325 right here. Most of you are in section 1, but it doesn't matter. It's the same. So you see that total enroll, it doesn't make sense. It's more than 325 and 10, but oh well, it's actually 18. So ET 325 is going to be April 30th from 10:30 to 12:30. So that is Tuesday. And if you look at the classroom, it says ML 114, but I guess I never got the message. So we'll just do it here. We'll come to this classroom.
ML is the one that you can first time.
The first time, yeah. Then everybody said, "Oh, it's too far of a walk across campus." So we moved it over here. But that's the physical location that we're going to be. So you're going to be allowed a full formula sheet, meaning 8.5 by 11 for all the stuff that you need. It's going to be less challenging, I think, than, in my opinion, than a regular exam because we only have 2 hours, right? All this, the schedule stuff for finals is all set by the Office of Student Records, including how long you have. That's all determined by somebody else. So that's the kit and caboodle of it. Again, you can use MATLAB or your calculator. I'll bring plenty of sheets, but it's going to basically highlight, one or two major topics from each of the exams. Doesn't include Bodie plots because we just did one class on Bodie plots. But hopefully the Bodie plot stuff will help set it up. If you do have it on the FE, you'll be able to at least counter being able to do the approximations. Because most people, when you do Bodie plots, you forget that scale factor thing. You go up or down at the break frequencies, but you forget that there's a scale factor. And sometimes people don't realize there's a phase shift plot with it as well. So you would need to include that as well. Okay. So here's the exam. And this is basically just a summary from the other 3 exams. It makes it easy to write if it's just a summary, right? So your key concepts: solve differential equations using Laplace. That's the first one, right? That's been a minute since we've done those. But hopefully what you see now is it's actually pretty straightforward or pretty efficient to use Laplace because we did the whole semester. We didn't even have to write differential equations. We just used Laplace to go ahead and simplify things. So you don't have to use the tables if we can stay in the Laplace domain. So as much as we can, we live in the Laplace domain. That's why we use final value theorem, steady state errors. When we were trying to look at performance characteristics, we came up with zeta, and we came up with the settling time characteristics to go ahead and allow us to pick points off the root locus. So again, we just stayed in the S domain, but we could say, what's the settling time need to be, or what's the percent overshoot going to be? And that's all based on the Laplace domain equations. We did transforms. So that's just doing a transform, which is transforming the input to the output. So we have a V out over a V in, an I out over an I in. You can do anything you want. And what we learned when we did some of our mechanical system modeling is we could apply a force, that was our input, and then the corresponding output could be a change in position of a body or a mass. We also did the modeling case where we looked at a permanent magnet DC motor where we could apply a voltage, and then the corresponding output would be able to give us a transform of what the voltage on the output would be based on that applied voltage. Okay. We also talked a little bit about poles and zeros, but then we also did op-amp circuits. So we just did op-amp circuits by analyzing them, and all we did was replace resistors, capacitors, whatever. We just replaced them by impedance values, Z. And then at the end, when we had an easy to work with equation, we substituted in those resistors and those Laplace domain equivalent capacitors or inductors. We can do either one. And then we just do the algebra to simplify the equation. So just do negative RF over RI or negative ZF over ZI. And you can do the transform analysis really easy. Op-amps are really efficient for doing that. Then we went to differential equation transfer function, right? So if we have a transfer function, if we have a differential equation, which we're give us an output based on an input or some input signals, we could do the transfer function for that. So we don't actually have to do circuit analysis or mechanical system modeling. We can be given a differential equation. And if you think about that, when we do the mechanical system or electrical system modeling, we're actually figuring out how to write those differential equations. So somebody has already done the work for you and did the model and did the calculations which is necessary, which is really useful because you might not have the expertise to be able to come up with a model. Like if I said, go look at this moisture separator reheater and figure out what the transfer function is based on valve position input based on the output temperature of the steam, that might be really difficult. But a mechanical engineer or maybe somebody who specializes in thermodynamics, could be a chemical engineer, you could go ahead and you could actually put those two together and then they could come up with a model. And all you care about is, hey, I just have to control the valve a certain position. So you do your own transfer function for the control valve position. So that's the advantage of using differential equations because somebody else does it and you can use Laplace and you can solve for that. Not a lot of detail. This is just a review. So hopefully moving forward, when you look at resistors, inductors, capacitors, you'll just think about, what am I doing here? Well, everything can be done in the Laplace. And when we do things in EET325 or in AC circuits, you're doing a very specific application of Laplace. If you remember that if I have a capacitor in the Laplace domain, that is negative J over, sorry, it's over omega times C is what we have. Well, if I plug in over here, I know that J omega is equal to S. That becomes 1 over J omega C, which is equal to negative J over omega C. These are the same. So AC circuit analysis is a very specific application of doing Laplace. Okay. So if you look at circuits now, and you don't just look at them as inductors, resistors, or capacitors, or you look at them as just impedance devices, and it has a Laplace domain impedance, or it has an AC, steady state representation or complex frequency impedance, we can go ahead and do that. So here's the equivalence if we do them in this circuit, 1 over SC, S times L, R. If you ever get stuck and you can't remember, do this work here, right? What is the capacitor like in terms of this term? It's negative J times X sub C, which is negative J over omega C, which is equal to 1 over J C. And we know that S equals J omega. So we end up with that. Because most of you all will be more familiar with the steady state circuit analysis approach than you will be Laplace, because you don't do Laplace all that often. Okay, that's kind of a summary. So a lot of the stuff we've done to this to this point is sort of review, maybe not the differential equations stuff, but it's based on material that we did a lot of in 324. Now we actually did some new systems, mechanical systems, because if we have the same approaches, the same concepts that we do for electric circuits, linearly independent, and we can write a few equations, we have mass, damper, spring, we can come up with analogies to go ahead and figure out how the effects of acceleration or applying a force is going to move a body, and some things are going to prevent it. So we can see that the mass, it is taking energy away to get it to move. So that's our inertia constant. If we have a damper, it's taking energy away to move the lines in either direction, or move the actuator. Maybe I guess we call it the actuator. And we can do the same thing with the spring. So we're just writing the differential equations using either Newton's second law, the viscous friction rule, or Hooke's law, and then we can just convert those to Laplace. We don't need to solve differential equations to do that. Everything in mechanical systems, at least for what we're going to do for this class, is going to be force balance. So finding a point and then summing the force balance at a particular location, kind of like doing KCL. You have a node, and then you sum the currents in and out. It's the same thing for force balance. You have a node, and you're summing the forces in and out, and they have to be equal to 0. We could also do that with rotational systems. So if we have rotational systems, it's pretty similar, but instead of forces, we're now talking about torques. But everything is exactly the same. It takes energy to get that mass to rotate. Same thing with a damper. If we're trying to rotate something and we're doing it through a viscous fluid, we have to go ahead and do that. The torsional spring is a harder one to see because obviously we can't keep elongating the spring. But one of the things that people don't realize is when you rotate something, a lot of times you'll actually have it pushing against something, wants to move in this direction. That's why sometimes we call axial bearings, which basically just prevent it from the shaft from sliding out. It's the same thing over here. You can actually use these bearings that are spring washers, and as it tries to rotate, it tries to rotate this way, and you can push it back, and that's the same concept of rotational friction from a spring, essentially. But same basic equations, but now we use torques. And we do the same thing, converting them to the Laplace domain. And then you just do torque balance. So instead of force balance, you do torque balance. DC servo motors, we won't get into that. There was a fair amount of derivation. But what we saw is that given an applied voltage, so if we know the applied voltage of a system, not the current, but the voltage, we could have certainly written this as a function of current. But voltage is, typically more useful, right? We turn on the voltage source and we measure the current that's going into it. So let's do this in terms of voltage. And given an applied voltage, we will get a corresponding speed output. We don't care about position because this machine rotates forever, essentially. So its value of theta, its angular displacement is just going to keep going and going and going. But its rotational speed can stay constant if we apply a consistent voltage. So we have a transfer function. And here are all the different terms that we have. RM, LM, EA, KT, KM, J, and B. Okay, so these two are part of the electrical circuit. Everything else, the KT and all those stuff are part of the mechanical circuit. So that's another really good thing about a control systems class, is because it's a way of transferring mechanical and electrical and work in neither discipline. We reintroduced pole zero maps this semester. Why'd we do that? Because we saw how much time we lived in the S-plane. So having our pole zero maps and having a really good understanding of pole zero maps allowed us really to translate and actually do root loci plot. So we looked at finite poles and finite zeros. And if you remember last semester, I warned you, I said, well, there are also infinite zeros that we haven't considered. And if you can understand now why I harped on that so much, is because those infinite zeros allow you to do your root locus plots. But we really need to have a good handle on pole zero maps. What is a stable system? What is an unstable system? What is a marginally stable system? And then also understanding that we had to have complex conjugates. And then we started to understand a little bit about if we were on the real axis, how that equated to settling time. We didn't necessarily know what was going to happen in terms of percent overshoot. We needed a little bit more discussion on that. But at the very least, we had those concepts in, and we got that from here. Okay. First order system response. We did that a lot last semester, but we actually developed some equations because last semester we always went and back to the time domain. So we always got a time domain function, an f of t function that would give us the complete waveform. This semester, what we were thinking about more is what is more useful to us? Well, I don't know if I really care about a first order systems response in terms of, what it actually looks like. I'm more interested in how long does it take to reach its settling time within its plus or minus 2% of its final value. Or how long does it take to rise from 10% to 90%? So those equations were far more useful for us to develop. So we worked with them. And then we saw first order system was good, but we also have possibly a second order system. So now we had to do a lot of work. And then we had these equations based on zeta and omega sub n. Zeta is our damping ratio, and omega sub n is our undamped natural frequency. And with that, we could use this to design parameters. So if we had a second order system that had some overshoot, which means it has complex conjugates for roots, we could actually say, well, let's limit the percent overshoot to a certain value. Let's limit the peak time. Let's limit the settling time. So we had a lot more equations to do. But if you notice, all these equations are based on zeta and omega sub n. Okay. And this is when we started to introduce the concept of looking at our pole zero maps. Where on the pole zero maps does omega sub n show up? Where does the zeta show up? And so we could actually start to use that. We use that a little more in root locus, but if you recall, we actually had those plots that showed the physical locations. Some block diagram math where we just did combining block diagrams. Why do we do that? Because we can analyze systems that are really complex by taking them down and chunking them into smaller pieces. So if I have a really complex paper making machine, or paper making system, I can look at each individual part. I can look at a heater part. I can look at a roller part. I can look at a compressing part, whatever it is. And I can individually build those blocks because I can handle understanding that one piece of the system. And then I can move on to the next piece and I can do that. And I can do all these different systems or parts of the system independently. And so then I have an overall block diagram. And as long as I don't have significant interstage loading, then I can assume that loading between the two stages is not impacted. Now, is it always the case in the real world? Not necessarily, but that's a good way to start off, is to make your assumption and to at least get some result. And then once you're done, you can combine those blocks to get an overall system transfer function. Because if you recall, all our work this semester was based on either doing the closed loop transfer function to get the characteristic equation, or doing the open loop function to get the steady state error, to be able to do the root locus plot, and even to do Bode plot analysis. So we still needed a bunch of work to simplify those blocks down so that we're actually able to do something with it. And this is the math that we did. And then we were silly at the beginning, but we said, let's do Ruth Hurwitz. And everybody said, well, maybe I said it, but I said, why would we do Ruth Hurwitz if we have MATLAB or your calculator that can do root calculation or root solving for us without any problem? I said, well, what if you don't always know the parameters? What if you can design a parameter to figure out what the characteristics you want? So we still teach Ruth Hurwitz because it gives us a range of stable gain or unstable gain that meets certain criteria. So doing Ruth Hurwitz was really helpful because it actually allowed us to do a calculation without actually knowing the full characteristic equation, what that was going to be. We also realized that we actually cheated, excuse me, and used some of that information to help us do nice looking root loci plots. Okay. But the approach is pretty similar. We take our characteristic equation and we simplify it down so that we have S to the third, whatever, S to the fourth, whatever the highest order S term is. And then we go all the way down to the S to the 0. And then we identify our rows based on the highest order S term. And then we go all the way down to row S to the 0. And then we populate the columns, the first two rows with the columns of the first two rows by alternating the coefficients. Don't ever skip a coefficient, meaning if there's a 0 there, it needs to end up in our system, in our Ruth Hurwitz. But remember, if a coefficient is 0, unless it's S to the -1, right? If there is no S term with it, if it's a 0, then we know by default that system has to be unstable. So if any of those terms vanishes, you don't need to do a Ruth Hurwitz if you're trying to figure out how many poles in the right-hand half plane. We know, or if there are any poles in the right-hand half plane, we know by default it's going to be unstable. It's the same thing if we have a sign change in our characteristic equation. If they're not all plus or they're not all minus, then we have an unstable system, and we don't need to do our Ruth Hurwitz unless we're trying to determine how many poles are in the right-hand half plane. As long as you have one, it's unstable. So normally that's the question. Is this a stable system? Which is another way of saying, are there any poles in the right-hand half plane? If we had a couple of problems with Ruth Hurwitz where we'd have a 0 in the first column of a row, only a 0 in that first column, what we had to do to continue, because when you do when you go down to the next row, it'd be 1 divided by that 0 you just calculated. You can't do that, right? That's infinity. So what we did is we substituted the variable e, which allowed us to continue with our calculations. And then when we were done, we would allow e to approach 0 and then see if we got any negative numbers. Which is different than if you had a full row of zeros. So all the terms in the row are zeros, which means you had to use the auxiliary equation. So you grabbed your row of zeros, you figured out the coefficients for that by going to the row prior to that and using the coefficients to set up your auxiliary equation. Then you would take the derivative of that equation, set it equal to zero, not set it equal to zero, just take the derivative of that equation, and then that would give you the coefficients that you would use to continue with your Routh-Hurwitz approach. But normally what we found is if we had a row of zeros, then we would have a marginally stable system. Okay, and using that auxiliary equation allows us to calculate, the J omega crossings. Steady state error. It's all based on doing the open loop game because we want to see the difference between what we want and what we've got. So we don't want the closed loop, we want the open loop. So this is the first time that we actually started to use the open loop transfer function where we use just G times H. And we were looking at it and we said, wow, let's come up with a standardized approach. So our steady state error was based on using these constants, a position constant, a velocity constant, and an acceleration constant. And hopefully it screams at you, if I have a position constant, it's just the limit as GH approaches, S approaches zero for GH. Take the derivative of the position constant and get the velocity constant, which just means multiply by S. Take the derivative of the velocity constant, which gives me my acceleration constant, which means takes the first derivative of Ka or the second of Kv, sorry, or take the second derivative of K sub P. Once we had that equation or those values for Kp, we can just use those to very quickly find what our steady state error is. So you have to be able to calculate those constants, and then you can plug that in based on, what value it is. Notice it is determined by the type of the system. System type is the number of integrators or the number of poles at S equals 0. So look at how many zeros or poles you have at S equals 0. That defines the type. And then you can quickly go down into those columns to figure out what my constant's going to be, as well as my steady state error. So for a type 0 system, you can see that my step input, I calculate the K sub P, limit as S approaches 0, G times H. That gives me the value. And then I can solve for the actual steady state error going here. I don't need to do any more work over here because I know for a ramp input or a parabolic input, the case of those K values is going to be 0, and I'm going to get this infinite steady state error. So you really just need to calculate this and then just pull these out of the table. You can certainly check it and see what you want. If you plug in for a type 0 system, a ramp input, you would confirm that KV equals 0 and ESS is going to be equal to infinity. Okay. We went back to algebra for this next topic and polar and rectangular math. Why do we do polar and rectangular math? Maybe you all got it, right? It's been a minute since you did AC circuit analysis, but it's very handy for us to do polar and rectangular math for AC circuit analysis, right? We do that a lot, but also to be able to do Bode plots and to do root locus plots, because we were so focused on trying to find magnitude and angles for both of those, right? Root locus plot, it always has to be one at an angle of plus or minus 180 is for a valid root. And Bode plots, we always know that we're calculating the magnitude changes as well as the angle changes. So we have to pull out the magnitude and angle parts of it. So we did some calculations to do that. And we saw multiplying or dividing complex numbers that are in polar form is really easy because you just multiply or divide the magnitudes and add or subtract the angles. You can do everything you want to in rectangular numbers, but you're going to have to FOIL everything. And then you're still going to have to convert it back to Laplace. Convert it back to polar. And what we see is once we got comfortable with this, it was actually much easier to do Bode plots because when we looked at our Bode plots, we did magnitude and angle. And if we did 20 dB, we don't even have to add or we don't even have to multiply or divide magnitudes. We could just add or subtract. So it makes that math even easier. So that's why I spent enough time, I think it was half a class, to go over and review complex math, but it really is just all based on right triangles. All the stuff we did is right triangles. And then root locus starting and ending points, right? Start at a pole, end at a 0. Pretty easy. as long as we have a 0 to end at, that's why we have to have a number of infinite zeros. So the number of total poles always equals the number of total zeros. They have to be the same because we can't even do a root locus. And when we did our limit functions, we saw how that worked. Here are our calculations for if you do have poles, zeros at s equals infinity. Here's how you calculate those angles to get those asymptotic angles. Remember what R is. R is plus or minus 1, plus or minus 3, all the way up to n minus m. Okay. So that's our angles of the asymptote. This is where the asymptotes originate, and they always originate in the same location. Just sum the poles and the zeros and subtract the sum of the zeros and divide it by n minus m. And then if you actually have to leave the the real axis, then you had breakaway or break-in points. And that was all based on drawing your preliminary root locus and seeing where it lives on the real axis. Remember, it always lives to the left of an odd polar zero. So if you draw that initially, you can go ahead and determine, do I need to calculate breakaway or break-in points? If you have complex poles, complex conjugate pairs of poles, or complex conjugate poles of zeros, you know that you are arriving or departing at those complex poles or zeros. So that was just making sure that you equal the rule, which is you have to be equal to plus or minus 180. And the fact that you're actually subtracting in this direction or in this direction is all based on the angle of departure is when I'm leaving a pole. So that's why it's the theta z's minus theta p's. Whereas when I'm arriving to a zero, so it's the opposite. So I'm solving in the opposite direction. Oh, sorry about that. I did a typo. I copied something over, so you can ignore B. But number 1, or A, determine the number of poles on the right-hand plane. Got a bunch of tools in your toolbox to do that. Number 2, given some block diagrams, specify design parameters that meet criteria. So percent overshoot, settling time, et cetera, et cetera. If I give you a characteristic equation with adjustable parameters, make sure the system stays stable. So you should be thinking about how you tackle those. If I want an ESS, got to do some design to make sure that I am reaching that ESS. And lastly, identify regions locations on our S-plane plot that meet criteria. Pretty cool, huh? If I had put these test questions at the beginning of the semester, what would you have done? Walked out the door?
Very simple plan.
Oh, good.
No,
But it's kind of cool though, right? It's like this is what you hope to get when you get educated. You actually start to see, you get the background and the information. It doesn't seem so intimidating, and you have the ability to do it. So you should applaud yourselves, right? Because although this class isn't super challenging, I don't think it's based on a lot of math, but it's all based on math that helps you kind of walk through the process, right? There isn't, like in my 321 class, you really got to do a lot of background information on circuits and all that stuff to really understand what's going on. In this class, it's like, let's just use some math to be able to solve some problems. That's basically what control systems is. Solving problems that engineers can handle. So taking it to math and then doing math on it. We do the same thing in other classes too, in circuit analysis, but we have to model those systems. So we need a lot more information to be able to do that. But in this type of class, you don't have as much. So questions about anything? Ready to be done?
Yep.
Are you gonna provide the chat for the block diagrams?
Well, I don't think I need to, because there's not a specific test question that does that. But be able to do the basic ones, like a feedback loop. Should be able to do the G over 1 plus GH. That's probably the only one you need. And hopefully by now, you've done it so many times, you're kind of sick of doing it, so. Anything else? Well, I just want to thank you. This has been a wonderful class. I mean, we've had tough years with COVID and students and stuff, and I think all the faculty here agree that you guys have been a wonderful class. Folks, I should say, not gender specific, but we really appreciate your enthusiasm and contributions to the class. It really does make a difference. I mean, we all love to teach and we all want to be here, but when we have students who want to be here and care, and we're not stuck in our homes doing everything remotely because of COVID, it definitely changes the mood and the attitude. And so I do appreciate people coming because I do make the classes, available online and in person. But the more people that attend the live class, it makes it a lot more fun for me. But this is my job. And so that's why I'm like, you know what? I'm going to just make it so that anybody can do the class remotely. And I feel like coming to class sets you up best for your long-term success in the class. You just get more out of a class coming in person. I'm pretty focused when I do stuff, and I have meetings every once in a while. And I realize if I turn my camera off, my focus is diverted to someplace else. But if I have my camera on, I'm paying attention, I'm engaged. But if I'm in the class, in the class or in the meeting live, you can just get body language, you just get more information, you're just more engaged in the conversation. So that's just life advice too, when you get out on your first job, especially when you're introductory, entry-level stuff, having those times and working with people and doing face-to-face meetings, even if you're doing senior project stuff, getting together as much as you can is just going to make such a big difference, in my opinion, in your careers. Somebody who's old like me, you don't get as much value out of having those interactions, because it's not that you can't teach an old dog new tricks. It's more about the thing, which is I don't need a lot of the other stuff to help me be successful, because I've learned a lot of things by doing exactly what you've done. I've spent 25 years or whatever in the field or working in meetings where you had to do face-to-face. This whole Zoom world is only in the past 4 years, right? Did anybody here use Zoom before COVID?
Yeah.
And the world shut down, at least campus shut down on March 27th of 2020.
No, 13.
13th?
Because I remember my first 15. I picked up for my birthday.
Okay. So what I did back before then, I used to record all my classes. So I'd have a camera in the back of the room, because Zoom was kind of around, but nobody really used it. And it's only when COVID, everybody got booted off campus, is that we actually had a much better technology. It'd still be nice to have cameras so we could see the interactions, but I don't think anybody does it now. And a lot of people, when they talk about remote work, you're starting to see office buildings in big cities are starting to have problems with vacancies because everybody's working from their house, which I get. I think that's a good idea, but I can tell you from having 2 kids that have had various medical needs over the past week, one emergency dentist visit and the other one with 2 or 3 doctors, like urgent care doctor appointments. The quality just isn't there. People are working remotely. They're not available to help you. The staff just isn't there. And so losing out on that interaction with humans, I really think it's negatively impacting people. And I'm concerned as we move forward, everybody wants to work remotely. Well, who's going to clean your teeth? Can't do that via Zoom session. Who's going to change the tire in your car? Or who's going to fix your flat? Like I've had a slow leaking tire in my car for 2 months. And I went to go get it repaired, and the organization just to get an appointment, where before you could just walk in, hey, I got a slow leak, can you fix it? No problem. Now you got to schedule appointments 2 weeks out. My son, who had a dental thing, he has to go back to the dentist. And it was one of those things where he can't even get this thing that's supposed to be important for him. He can't get it done for 2 weeks. And the worst part about it is he had that type of retainer, but a spacer thing that's glued into his mouth. It came out on one side. So you think, hey, call the doctor. What do we do? The dentist, what do we do? No, you can't call the dentist. You got to email him. And then he emails back and forth. Call me. I don't know what I can do for wiggling. I need to talk to somebody. You're telling me to wiggle it off. What if that hurts him? What if it yanks his tooth out? I don't know. I'm not a dentist. That's your job. And so that's the thing, is that he would email, or she. I don't know if it was a he or she, but that's I think some of the concerns that you all and we all will have to deal with as we continue on. So I'm not saying you shouldn't work remotely. I think it's great. I mean, I know for me personally, I find it a lot more effective than if I have to commute, 30 minutes each way. And then like, if I'm at home and like, if my son needs something for whatever reason, I can walk 5 minutes and go deal with something and then get back to work. Whereas in the past, it's like, okay, I have to do daycare, this, whatever, just these types of things. So it makes it much more difficult. So that's part of the things that you want to think about is how can you be the most successful? So for those of you who are graduating full time, don't say necessarily, hey, I want to take that remote job, because yes, there are some advantages, but you're going to lose out on a whole lot, especially those first careers. For interns, can't recommend enough, if you can, unless you live a long way, going to the office every day, being there, sticking around later. People are going to notice those things and they're going to see this person's available. I need some help with something. I'm going to go over and ask, hey, Joe, I'm just saying Joe because there's no Joe in here. Can I get you to help out with something? Because I see you're here. Do you have time to help me? I need help. Sure. What do you need help with? Even if he asks you to mop the floor, or she, you know what? If that person's willing to pay me whatever billing rate I'm getting, I'll mop the floor. I think I shared with the story where I was living in Baltimore. It was a Friday night at 5:30, and I thought I was the last one to leave. And my boss was there standing in front of the photocopier with reams of paper all over the place. I'm like, 5:30 on a Friday, what are you doing? Oh, I got to get this report out to FedEx by 8 o'clock. And I could see him, and nobody was there helping him. He was doing it by himself. It's like, would you like some help? He said, oh my God, that would be great. Because he was too proud to ask for help. And so I stayed and photocopied him for 2 hours. And he was just like, I was number one at that point. You know what I mean? Just because I was there to help him. And the best part about it is he was willing to pay. I think my company was billing me at $130 an hour. So he was willing to pay somebody $130 an hour to hit print. You know why? It wasn't because I was the best press print person in the world. I was the best print person at the world who happened to be in that office on a 5:30 on a Friday. So what's the message there? I was there. I was available. And there are so many times when a crisis or a crash comes through, if you just happen to be there, that's when, it's like you get the star because you helped out. You don't even have to be perfect. What can I do to help? And that's when you're going to learn. And that's how you get promoted. So same thing with doing well in school. If you're around, if you're coming to class, you just get more out of it. Just do more stuff. I'm not pointing at any particular student. Yeah, this is not any based on any student. I'm just telling you, this is what has worked well or really well for me. And you get to decide on your own what works really well for you. You can try hybrid, yeah, but I'm telling you, the more you can be in the office, you can see things, you can look at things, you're just going to be more successful. And it's too easy to have your computer up and in the background, you've got, I don't know, YouTube, looking at Schmeemobiles or something like that, right? I mean, whatever floats your fancy.
Do you know if you are graduating in EET325? Because I know there was a decent amount in senior projects, but I feel like half of them are like, I'm coming back in the fall.
Well, they might, so remember, they're not graduating. So what you do a week from Saturday is, it's not graduation, it's commencement, which is to acknowledge that you are most likely leaving the university, but you're not necessarily graduating because you might have some classes to finish. And so even just advice about that, you and your families have either paid or spent a considerable commitment to get you out of here. So if you aren't necessarily graduating, or if you aren't, if you're close, but if you're going to be graduating in December or the summer, attend. It's one of the very few times in your life that everybody is happy for you. Think about it. You're getting married to somebody. You think your partner's great. What do your parents think of that person? They might not like that person very much. So they might not be happy for you. But at graduation, everybody is so happy for you because they just see a future that's laid out for you. And so nobody is spiteful. No, there's no drama. There shouldn't be any drama. Sometimes there is, but generally there isn't any drama because everybody is just so happy. So that's one of the graduations is literally one of the very few times in your life, and everybody in your life is happy for you. Nobody, somebody would give you a hard time, but nobody's gonna say, what are you doing? They might say that when you start at college, but when you finish, they might be like, they'll be like, wow, you did it, you graduated. That takes a big commitment. That's a lot of time. Congratulations. So some people might be like, well, yeah, but I've been working for the last years, making $50,000 a year, working on cars, which is great for them. But this is about you and moving forward. And so this is your experience. So don't let people take that away from you. So if you don't want to go to the full graduation, at least go to Francis Crowe. It's a little more intimate and familiar. So I would encourage you to attend that. That's really good. And it's still just SET. They were talking about doing the entire College of Engineering all in one space, but that would take like 17 hours. So you just do SET.
Ceremony.
Yeah. It's not graduation. It's maybe half an hour to an hour. But you get a medallion, you get inducted to Francis Crowe. There's a little, meal after. You get to meet the faculty or introduce your parents, family to the faculty if you want. You don't have to. And even those who aren't graduating, if you have the time, some of these people are your friends. You may never see them again. Just to send them off. Nice thing. Congratulations. It was good knowing you. I'm really pleased to have met you. I wish you nothing but success. And that does two things. Those people who are graduating makes them feel good. What's the other thing it does? In 2 years, hey, I'm looking for a job. I heard your company's hiring. Could I maybe send you my resume? Or have you heard about job opportunities? That's called networking. And so people will remember those of us or those of you who go that extra mile without a lot of work. You might have to stick around a couple extra days after finals, but the idea is that it just helps to keep that network going. So the more stuff you can do, the better off you are. Just my opinion. That's what life is about. There was a book, Andrew Carnegie, how to make friends and influence people or something like that, and it's about networking, just how to get those networks done. You don't realize it until you need it. Wow, like for me, I'm fairly handy and I know how to do a lot of stuff on my heating system. So I've never had to bring in a plumber to do stuff. I do it all myself. Until that one time when I'm not around and major plumbing things happens. Now I don't have anybody. Or I want to get some plumbing work done because maybe I want to add a bathroom. And it's too much work for me. Good luck finding somebody to come do it. They have no relationship with me. So why would they bump some of their customers that give them repeated work over and over and over again to do work for me? Doesn't make any sense. So that's about networks and having relationships with people. I'll shut up now. I've been sick of hearing me all semester, so. If there is nothing else, I wish you all the best of luck. See you all on Tuesday. Make sure you send me an email. You can do it online if you want. But yeah, that's it. So take care, everyone, and have a wonderful day. Hopefully it warms up.
Thanks, Paul.
Thank you, Paul.